Welcome, I'm Jim Corkins, and we are continuing on with your course. We are starting sort of a new section, which is about the electric field. So we had talked before about the force acting on a charge, and when we wrote our equation, we had written it like this: Q1 K Q2 divided by a distance apart squared. Now, I had mentioned this several times, but this right here is the electric field of Q2. So now we are going to just look at those electric fields, and we're really not going to worry about a force acting on a charge right now. We're going to just look at what is the electric field, what causes it, what are the concepts that we know that are scientifically understood about this electric field due to positive and negative charges. So that is what we're going to concentrate on right now. Now, again, if you haven't done your reading, please do so, because there's a lot of nuances to electric fields. Okay? Now, in this section, we're going to go through all of these things. Okay? And if you're in Physics 131, we are going to later on go through continuous distribution of charges and on a line, but also on areas. And even we might do a volume integral. All right. So let's start off, and we're just doing an introduction. And here are the basic rules for electric fields. All right. So electric fields are vectors. So we are going to still have to use an absolute value. The direction of the electric field being positive or negative, again, is going to be in terms of up and down and left and right. So positive x, positive y, negative x, and negative y. And you will have to determine that direction on your own. So the sign of the charge does not necessarily determine the direction of it. That's why we have it in absolute value. You have to artificially kind of add if it's going to the right or to the left, okay? And we'll talk about that. Incidentally, if we did have a force that was written like this, a force equation, which was Q1 K Q2 all over R squared, where this is the electric field right there. So in other words, we could say this is Q1 E2. Well, if we take that force right here and we divide it by Q1, meaning that we're getting rid of it, now we're just looking at the electric field due to Q2 that is acting on Q1. So that's why it's written like that. Okay. The units of electric fields are newtons per coulomb. When we get into voltage or potential, electric potential, we will also be referring to them as volts per meter. So depending on how you're solving the problem, you could be using volts per meter or newtons per coulomb. Typically, if you see a volts per meter, you're going to be using potential or energy to be solving the problem. But if you're using newtons per coulomb, that kind of lends itself more to forces and force diagrams. Okay? Now, here's rule 1, where the density of the field lines means a stronger electric field. In other words, the larger the charge, if Q2 goes up, then the electric field is going to go up. So the electric field is analogous to Q2. So if Q2 goes up, if Q2 goes up, Q2 in this equation right here, K Q2 over R squared, if that goes up, since it's directly proportional to the electric field, then the electric field is going to go up. All right. Now, distance is inversely proportional to the electric field. So if you are measuring the electric field further away, if R squared, or if R goes up, the electric field is going to drop by the square of that amount. Okay? So that's kind of what this means here. We'll talk about electric field lines and their density, but essentially these two rules mean this. So the number of electric field lines entering or leaving a charge is proportional to the magnitude of the charge, right? So if you have a 1Q charge, it's going to have half of the electric field lines. Well, it'll be represented by half the electric field lines of a 2Q charge, okay? And again, the further away you are, typically with a point charge, the further away you are, the weaker the electric field. And that means because there are less lines going through an area, okay? Now, electric field lines emanate radially from an object. So if it's a circle, you'll see it look like spokes on a wheel, right? And if it's a positive Q, it'll look like spokes on a wheel. In other words, these electric field lines are also perpendicular to the surface, okay? Now, with electric fields, they could be represented as vectors, and they are parallel to the electric field lines, to the electric field. This should say parallel. I apologize. It says parallel in your notes. So if you have electric field lines represented this way, you could write a little vector at this point and just represent a vector at that point. Okay. The longer the vector, the stronger the electric field. So just like a velocity vector, the longer the velocity vector, the faster you are going, right? So similar idea. Finally, electric field lines point away from positive charges and towards negative charges. All right. So let's go through each one of these 4 points in detail. All right. So first off, we have, this is a picture. So this is a picture of a positive Q charge. And let's say you placed a sensor right here and you want to measure the electric field at this point in space. Well, that electric field is represented by a vector. And so that's why it's got the vector head. And since this is a point charge, this electric field vector is going to be represented by KQ divided by this distance from the point source charge to where you place the electric field sensor. Now, the electric field sensor doesn't have a charge on it. It just detects electric fields. Okay, so we are thinking of the force equation, but just without the Q1, right? And again, that the units will be in newtons per coulomb. Okay, so let's go ahead, and they're in the notes, in the PowerPoint notes. If you click on this in the PowerPoint notes, this is a picture of your PowerPoint notes. It'll send you out to this website right here. Okay, so it's also in the notes section. So if I go to this area in the notes, I'll make sure I add that to it. But as you can see in my notes, I could just click right here. Okay. So I just placed the website in the notes area here. So let's go ahead and this is the simulation. And you do have a lab about this situation. Now in the simulation, it's weird. Red, which is typically represented as a positive charge, that's actually the negative charge. If you look closely right here, those have little negatives in front of them. Okay, and the positive charge will be green. So I'm just going to go ahead and grab a little positive charge and place it right here. Okay, so it's kind of cool. You could drag and drop these little guys, and you can move these charges around. So this is the simulation, and we'll go through the simulation as we're going through these rules. Okay, so essentially here is what we're talking about though. So we're going to go ahead and I'm going to go back to that simulation. I'm going to click on it and put a sensor in outer space and detect the electric field due to that charge. Okay, so I'm going to click on electric field vector. Okay, and I'm just going to go ahead and put it right here. And notice when I clicked on it, a little vector popped into existence, right? So this is a +4 microcoulomb charge, and micro meaning times 10 to the -6 coulomb charge, and that is the electric field at that point. Okay, we could even put the values on that, although I don't want to look at the actual values of that. In the lab, I think you're supposed to hand calculate those. Okay, but you would take whatever this distance is from the center of the charge to here, and that would be r. And this vector line is pointing up and to the right, so it has an electric field in the x direction that is in the positive x direction, and it's got an electric field in the positive y direction. Okay, so this vector has two components, an x direction and a y direction, just like force vectors do. Okay, all right. Now let's talk about what I meant about the density of field lines. Okay, so let's just say you ran, you had I don't know, a meter stick out in outer space. You had a positive Q charge as a distance r away, and you had this meter stick. How many electric field lines do you see going through that area right there, that line? Well, I'm seeing 3, right? So I'm seeing a total of 3 electric field lines. Okay, and also you should note that the electric field that is measured perpendicular to this point. So if you notice, there's actually a little cosine related to this, and we'll get more into this when we get into the continuum stuff for Physics 131 students. But see how this electric field vector is pointing up and to the right? Well, only the component that is perpendicular to the surface, so, is the measurement of the electric field. The vertical component of this vector, which is the sine theta, if this is theta, only the cosine portion contributes to the flux. Okay, so again, we'll get into this when we get into Physics 131 and Gauss and things like that. But this electric field vector right there contributes to it, and this is E cosine of theta here, and this is just E because all of that field vector goes to it, right? So notice that the further away you get, the smaller the electric field vector. These two guys, these two E cosine vectors, are smaller vectors in sizes, and the one that is perfectly perpendicular, this electric field vector is perpendicular to this line, all of its vector contributes to that flux. So what you would say for that overall flux is you would it's analogous to adding up those field lines. E cosine of theta is the top one, plus E, which is this middle one, plus E cosine of theta. But if you're in physics 112, we'll just say that you see 3 lines going through it. Okay? You don't have to do these serious calculations, right? Now, if I move this distance, this meter stick, further out, 1.75 r away or 1.73 r away, what you could see is now there is only one line going through it, right? So it actually got weaker. So the electric field has become weaker, okay? And in that case, you would see a flux which would just be that E. Only this guy is going through it. Neither of these two guys are going through that meter stick, okay? So that's the concept of flux. That's the basic concept of flux, but that's how, when you get further and further away from the electric field, from the point charge, the point source or point charge, that electric field drops off. If you get closer to it, meaning if the R is getting smaller, meaning this meter stick is getting closer, then the electric field goes up by the square of that amount. Okay? Now, this next part, pretty easy. Suppose you had a negative Q charge and a negative 2Q charge. Well, this negative Q charge has 1, 2, 3, 4, 5, 6, 7, 8. This negative 2Q charge has 1, 2, 3, 4, 5, it's got 16. So there's 16 lines pointing towards it, right? Which means the larger the Q, the more Q's you have, the more charges you have built up, they're directly proportional to the electric field vector. Where over here, distance from the point source to the sensor is inversely proportional to the electric field vector by the square of that amount, right? So that's basically rule number 1. Okay. Let's talk about rules numbers 2 and 3 together. Okay. So let's say you had a weirdly shaped object like this here, and it had negative Q charges built up on the outside. If you notice that the electric field lines are emanating radially from this surface, right? So if I zoom in on this rounded part, and I'm going to go ahead and draw a black tangent line, okay, right, to the surface at that point, okay? So it's that tangent to the surface. If you measure that electric field line, it is perpendicular to that tangent line. So it's perpendicular to the surface. And so those are radial vectors. Okay. So the electric field lines emanate radially from the object, perpendicular to the object's surface. So you can have like these weirdly shaped objects, like this looks like a teardrop. And not only that, if these are the electric field lines, but notice if you put a vector here, okay, at this point, that vector, even though this is kind of a rounded field line right there, if you put a vector at that point, it's going to be pointing up and to the right. Okay, and notice that these field lines are close together. Meaning the electric field lines are closer together, therefore the electric field vectors will be larger, right? So where you see a lot of electric field lines, like in a teardrop in this case, there's a lot of charges built up right here. Well, then you're going to have a lot more electric field lines built up, right? And let's get a nice round it. If you put a sensor right here and you wanted to measure the electric field at that point, well, it's going to actually be pointing parallel to that electric field at that specific point, right? So I'm going to put a little sensor right here. And now if we take a tangent to that surface, which is parallel to that surface, that is going to be the electric field vector at that point. Okay? And the closer you get to it, the larger the electric field vector. So I put another one there. This vector is going to be a lot larger because it's closer to the source, which is that negative. So this line is represented by that negative charge. And notice the vectors are getting larger and larger as you get closer to the actual source, which is this guy, right? The inverse is true as well. So the electric field vector is large here, but notice that you're getting away from it. You could tell this is a positive charge because the electric field vectors are pointing away from positive charge. Electric field vectors are pointed towards a negative charge. So this positive charge, its electric field vectors are dropping off and getting smaller and smaller the further away. And that is because of the flux, right? So if we go over here back to our little simulation, I'm going to clear this. The only way I know how to clear it is just refresh it. Grab a little positive charge. I'm going to grab a 1 positive charge and put it right here. Okay. If I put an electric field vector exactly 3 units away, you get something that looks like that. A little itty bitty vector. Now, and notice it's pointing radially away in all directions. Okay? But if I refresh this now, and I get a positive 8, so this should be 8 times bigger, and I get that electric field vector, and I'm doing 3 units away. Notice that that is a lot bigger. In fact, it's 8 times bigger than the positive 1 microcoulomb charge. And again, it's pointing away in all directions. Okay? So, and that, again, if we do those surface lines, so this is the electric field. That electric field vector is parallel to the electric field line. And that's what we were talking about there. So, okay. Now, moving over here, electric field lines, again, can be represented as vectors. So here's the electric field lines, and here's the vector form of those electric field lines. Okay. So notice that the electric field vectors are, since this is a positive charge, they're pointed away from the positive charge in all directions, and they're getting smaller and smaller and smaller as you get further and further away from that charge, right? And that is because this vector is so large here, because if I put this line right here, let's draw it again. Yep. I draw it that big there, and then I draw a similar line out here. Actually, let's do further out here. So this is distance from here to here. I'll draw that there. And then this guy is further out, so I'll draw that same length line. see how there's only one vector going through the line for this chart, electric field vector. There's only one line going through it, but this vector is representing 3 electric field lines going through it, right? So that's the relationship to flux and how the electric field lines and the electric field vectors are represented. Okay. Finally, as I had stated before, electric field lines are pointed away from positive charges and towards negative charges. Okay, so if you have a negative Q charge, all the electric field lines and those electric field vectors are going to be pointed towards it. If you have a positive Q charge, all the electric field lines are going to be pointed away from it. Okay, so going to our little handy simulation, I'm going to refresh this. I grab a negative 8 charge and I place it right here. Well, the electric field vectors are going to be pointed towards it. So it's 1, 2, 3. Okay, in all directions. 1, 2, 3. There you go. And then the further away you get, the smaller those electric field vectors, right? And the field lines, they don't necessarily, you don't have to represent them with a vector arrow. It does help to kind of reinforce this concept. Whoops. This concept here. So these are kind of the vector lines, but also a little bit of a vector. Technically, if I was going to draw the vector out here, I would have a small field vector here, and here I'd have a much larger electric field vector. At this point, I would have an electric field vector pointed in, and at this point, it would be a large vector pointing in towards it. Okay. So those are all the concept rules for understanding electric fields, okay? And that is all encapsulated by this one single slide, okay? There are some extra nuances that you should know, okay? So here again, we have a weirdly shaped metal object with charges built up on it, okay? So there's an absence of negative charges. So it's just the positives are built up on this. Okay. So notice that I had sort of mentioned it before that positive charges are built up more on the points. So in this area, you'll see more positive charges than you will see on these rounded sides right there that are larger sizes. And that is because the charges are just more packed together at that point, right? You will also notice if you did put an electric field sensor at the center of that metal object, it would show an overall electric field of 0, right? And you might have noticed this sometimes if you get into an elevator and you're talking to your cell phone, talking to your friend on your cell phone, and the doors close and your call will drop, right? Or sometimes if I'm driving into a parking garage, which parking garages are made of concrete and there's a lot of metal and there's rebar and things like that. That's basically a solid metal object, sort of, and my radio will lose its I won't have a radio signal anymore, right? So where these little positives are built up is because their neighbors are really shoving them together, right? And when it's nice and not as rounded, it's got a gentle slope to it, the positives or the negatives will have a much more, they'll be much further apart from each other, okay? One last thing is this. So dipoles. So suppose you had a hydrogen atom. So this looks like spiders fighting, right? Or giving each other's hugs, whatever you want to say. But if you have an electric dipole, so this is kind of a hydrogen atom, right? The overall net field vectors look like this. And really what is happening is the electric field here isn't really aware of the electric field here. They're kind of just creating their own electric fields. But when you put those two together and you look at the overall net electric field, it looks like this. So in reality, this negative charge right here is still just emanating an electric field, like a negative Q, that is pointed towards it in all directions, right? It's just doing this, okay? So its electric field is pointing towards it in all directions. And this positive Q over here, its electric field is pointing away from it in all directions, right? But when you take those vectors and you add them together, you get these weird rounded surfaces that look like this. So this is the net electric field. The two charges are still just doing this, right? But if you take a point right here, here's what I'm talking about. So we'll take like a point that looks like this. Notice that the electric field is pointing to the right. Well, if I grab a sensor, I'm going to put an electric field sensor there. You get an electric field due to the negative charge that is pointing down and to the right. And you get the positive charge that is pointing up and to the right. Well, when you add those two vectors together, it doesn't matter the order in which you do this, you get a vector that you get that, correct? So you started here, you walked up into the right, down and to the right. Your overall net electric field vector will just be pointed to the right. And that's why it looks horizontal right there, which is why this looks horizontal to the right. But really at this point, you have a negative charge's electric field vector is pointing down and to the right, and you have a positive charge's electric field that is pointing up and to the right. Take the net of that and you get a vector that's pointing just to the right. So these kind of purple lines are the net electric field vectors. The addition of the negative charge and the positive charge, okay? So, now, again, if you doubled the amount of Q's, this is double Q's, you're going to get double the field lines, which these field lines are going to try to start rounding about and connecting to it. So you'll see more electric field lines connecting to this. But really, again, this negative Q, if it only had 1, 2, 3, 4, this positive Q would have double that. And again, they're not really noticing each other, this positive 2Q. Its electric field vectors, oops, I should have drawn that towards it. Sorry about that. So the electric field vectors are pointing towards it by 4. This positive 2Q, its electric fields are pointing away from it, and it's got double the amount of field lines coming out of it. And they don't really notice the other charge. They're just doing their own thing. They're emanating their own electric field. But again, when you add them together, it starts to look like this, right? So that's what happens when you have a dipole, meaning a positive Q and a negative Q. That this would be a hydrogen dipole, okay? Right? And overall, the net field on this would be 0, right? If you zoomed out from this, you would have an electric field that would be 0. But anywhere in here, at different points, you don't have an electric field of 0. But zooming out, you would. With a positive 2Q and a negative Q, so this would be like a helium atom, and it would be more of a helium ion because it would need another 2Q here. But if you have an ion that is a dipole, well, now the overall net in this case is going to be positive. So if you zoomed out away, you would have an electric field pointing away from this atom in all directions. Okay. Now, if you have like charges, for example, two positives, those electric field vectors are going to, in between it, the electric field is going to be 0. Okay. And again, this is what the net electric field looks like. So here you have a positive Q. Its electric field is pointing to the right in all it's pointing away from it in all directions. And you have another positive Q is pointing away from it in all directions. If you take this point right here, okay, you'll notice that it's 0 right here. The electric field is 0 at that point. There are no lines covering each other. And what I'm saying is, at that point, the electric field here is pointing up and to the left. This electric field vector is pointing up and to the right. Well, actually, I think this electric field is not 0. It's actually starting to point up right here. So field vector is pointing up at that point. So if you take a look at this, you put a line here, you get like an upwards line right in between them. You add those two electric field vectors together, up and to the left plus up and to the right, you get an overall electric field vector is pointing up. Okay. In the center here, okay, well, you have an electric field vector that is pointing to the right. You have an electric field vector that's pointing to the left. Add those one-dimensional electric field vectors to each other. You started here, you walk to the right, walk to the left. You ended where you started, so that electric field is 0. But as soon as you start to deviate away from that, it starts to get pointed upwards. Okay? So that's why the electric field is 0 right at the center, but up when you're above it and down when you start to get below this center point line right here. Okay? Now again, with a positive 2Q charge, you just have, which this is going to be, those will be negatives because they're pointed towards it. You're going to just have more field lines pointing towards it. And they'll still have this kind of shape to it, but here you just have more field lines. Okay? Well, this is the very first part, which is the introduction to electric fields. I do believe you have a conceptual quiz about this, so this video will help you out greatly with that conceptual quiz. All right? I hope you have a wonderful day. Thank you.